So this is the last sum on heat balance sheet that I will be solving. This came in the May 2019 examination. So see, this sum is slightly different because see, there are two things which are different in this sum as compared to the previous sums. The first thing is the volumetric efficiency, right? So in this sum, you have to calculate the volumetric efficiency of the engine. So we will see how we do that. And the second thing that we have to do, see over here, what is happening? If you see, just a minute. See, if you see over here, we have to draw a heat balance sheet in terms of kilojoule per minute. So whenever we have to draw a heat balance sheet, what are the five things that are necessary? First is the thermal power. Second is the brake power. Third is the heat loss to exhaust gases. Fourth is the heat loss to coolant, and fifth is the unaccounted heat losses, right? So these are the five things that we have to find. So out of this, thermal power is easy to find. What is the formula for thermal power? Thermal power is mass flow rate of fuel into calorific value, right? See, we have mass flow rate of fuel over here, we have calorific value over here, so we can find the thermal power. Can we find the brake power? What is the formula for brake power? Brake power is braking torque into angular velocity, right? In this case, see, they have directly given us the braking torque. Generally, what did we have to do? Generally, they gave us the braking force and the dynamometer arm, right? So we did F into R, then we found torque, and then we multiplied it by omega. What is omega? Omega is 2 pi n upon 60, right? So we have both torque with us and we have our RPM with us. So we can substitute these values and we can get brake power. Here, see, rather than giving force, they have directly given us the braking torque. Okay, they have directly given us the torque. So we can directly substitute that value over here. So we can do that. We can find brake power. See, what is, I will just come to exhaust again. What is the heat loss to coolant? Okay, so how can you calculate the heat loss to coolant? It is very simple to calculate heat loss to coolant. What is the formula for heat loss to coolant? Q is equal to mc delta T of coolant, right? The heat loss to coolant is mc delta T of coolant. So what is mass flow rate of coolant? See, they have given it over here. Cooling water flow rate, that is the mass flow rate of coolant. I will write over here mc delta T of coolant. So they have given us the mass flow rate of coolant. We know that. We know the specific heat capacity of coolant. Yes, we know it is water. Water specific heat capacity is 4.18 kilojoule per kg Kelvin. And what is delta T of coolant? They have given the delta T of coolant also over here. See, cooling water temperature rise 35 degrees Celsius. They have directly given us delta T. So we can find the heat loss to coolant as well. But what about the heat loss to exhaust gases? See, in all the sums that we have solved till now, they had somehow given us either the specific heat capacity, or they told us those in the previous sum we used the calorimeter to determine the specific heat capacity of the gas, right? But in both these cases, we assume the exhaust gases as a single unit, right? See, exhaust gases contain a large number of different gases. It contains N2, it contains CO2, it contains H2O, it contains trace amounts of nitrous oxides, it contains trace amounts of carbon monoxide, it contains some amount of particulate matter and soot. It also contains some small amounts of sulfur oxides, aldehydes, ketones, and all these things are contained inside your exhaust. But we assumed all these gases to behave as a single unit, right? In the previous sums, it had a same specific heat capacity, right? In this sum, what they have done, they have divided these gases into two parts. Okay, they have divided these gases into two main parts. See, out of all these gases that you see over here, only H2O, okay, sorry, of all those gases, here is particulate matter. Out of all these gases, see, H2O is the only gas which will undergo a change in phase. What does change in phase mean? See, what is H2O? H2O means our water, right? What is going to happen when the water is above 100 degrees Celsius? When water is above 100 degrees Celsius, it will be in steam form, that is, it will be in vapor form, As the exhaust gases cool down, the temperature will go less than 100 degrees Celsius. So as soon as the temperature goes less than 100 degrees Celsius, what will happen? This steam will get converted into liquid water, right? And whenever, see, any gas liquefies, there is some amount of heat rejected by that. That is equal to what? That is equal to the latent heat of vaporization, right? That is what they have given over here. I will come to it in a minute. So what is happening in this question? What they have done, see, I will tell you. In this question, see, whatever your this is fuel is, every fuel is a hydrocarbon. So it is what? CXHY, right? It reacts with O2. It is going to give you what? CO2 plus H2O, right? Plus all those other gases. There will be N2, there will be NOx, there will be CO, there will be some other thing, particulate matter, aldehyde, ketone. All those things are okay. In this sum, what they are doing, they are telling us that all these other gases are acting just as gases. They are just gases. They are only in gaseous state. But this vapor is initially in vapor state, then it will cool down, it will get converted into water, and that water will again cool down, right? That is what happens. So what do we have to do? We have to calculate the heat absorbed by these gases separately. The heat absorbed by these gases should be calculated separately. They have given us the specific heat capacity of dry gases. See, dry gases specific heat capacity means all these gases which are not water. And they have given us a different specific heat capacity for steam. So we have to do two calculations for heat absorbed by exhaust gases. One heat is absorbed by these dry gases and one heat is absorbed by this steam. And these exhaust gases are always in one phase only. They are only in one phase, that is gaseous phase. But this H2O, it is in two phase. First it is in vapor phase. Then what happens? Because the vapor condenses, it gives away large amount of heat, which is the latent heat of vaporization, and afterwards it gets converted into water and it again loses some heat, right? So this is what is happening in this sum. So we will see this thing, okay? Don't worry, we will see how exhaust gas calculation is done. That is the one major difference, and the second major difference is volumetric efficiency. See, till now in no question had they asked us to find the volumetric efficiency of the engine. But in this question, they have asked us to find the volumetric efficiency of the engine. See, by now you should know what is volumetric efficiency. I have explained it several times. Okay, still I will explain it once. See, what is volumetric efficiency? Volumetric efficiency is the actual amount of intake air, volume of actual amount of intake air divided by the swept volume, right? How did we get this? Okay, to see if this is your cylinder, this is your top dead center, this is your bottom dead center, right? So this is your top dead center, this is your bottom dead center. Above the top dead center, what do you have? Above the top dead center is your clearance volume, right? This is my clearance volume. What is between top dead center and bottom dead center? This is what? This is my swept volume. So ideally what should happen? When the intake valve opens, all the intake air should come in and fill this entire volume, right? The intake air should fill this entire volume during the intake stroke. But that does not happen. Why does that not happen? Because during intake stroke, what happens? So these exhaust gases from the previous cycle, they also expand a bit, right? They also expand a bit. So this volume is occupied by the previous exhaust gases. So only this much volume is available for the new gases, right? New intake charge. So this ratio between the actual amount of air which came in, actual volume of air which came in, and the volume of air which should have come in, that is the theoretical volume which should have come in, is your volumetric efficiency. So volumetric efficiency is what? Actual volume of the air that came into your engine divided by the theoretical volume of air which should have come into your engine. And what is the theoretical volume of air? It is the swept volume. So this is volumetric efficiency. So how can we calculate volumetric efficiency? Well, to calculate volumetric efficiency, we need what? We need swept volume and we need the actual intake air volume. Well, we can find swept volume easily, right? What is the formula for swept volume? Swept volume is what? Pi by 4 d square into L, right? Where d is the bore diameter and L is the stroke length. They have given us, see, bore diameter is 15 centimeter and what is the stroke length? Stroke length is 30 centimeter. So we can solve swept volume easily. But what is the actual amount of intake air, right? We have to find actual amount of intake air also, no? So how can we find actual amount of intake air? We will have to see, look at the given data and see if there is anywhere any mention of air, right? See, over here they have given us air fuel ratio, right? What is air fuel ratio? Air fuel ratio is mass flow rate of air divided by mass flow rate of fuel, right? So to find mass flow rate of air, what will we do? Air fuel ratio into mass flow rate of fuel. Do we have air fuel ratio? Yes. Do we have mass flow rate of fuel? Yes. They have given it to over here. So we can find mass flow rate of air. What will be the mass flow rate of air? Mass flow rate of air will be mass flow rate of fuel into calorific value, right? It will be 2.4 into 22. But this is what? This is per hour. This is kg per hour. This is mass flow rate of air in kg per hour. Do we need it in per hour? No. We need it in per minute or we need it in per cycle, right? When we say volumetric efficiency, this is the actual amount of intake volume. But actual amount of intake volume in what? In one stroke, na? In one cycle, na? During our intake stroke, what is the actual volume coming in, right? So we need the amount of air which is coming in one cycle, right? So how can we convert it from per hour to per cycle? Well, first of all, what we'll do, we will convert it from per hour to per minute, right? How to convert from hour to minute? Divided by 60, right? In 1 minute, this is the amount of mass of air which is coming into the cylinder. In 1 minute, this is the mass of air coming into the cylinder. Now we what have to do? We have to convert this from per minute to per cycle. So what we can do? We can divide this by the number of cycles in 1 minute, right? We can divide this by number of cycles in 1 minute, right? If we divide the total amount of air that is coming into the cylinder in 1 minute and divide it by the total number of cycles in 1 minute, we will get what? We will get the mass of air coming into the cylinder in one cycle. So how can we find the total number of cycles in 1 minute? It is very easy. See, they have given us the number of rotations in 1 minute. There are 300 rotations in 1 minute and this is a 4-stroke engine. So what? When 2 rotations take place, there will be 1 cycle. 1 cycle requires how many rotations? 2. So when there are 300 rotations, there will be 150 cycles. So there will be 150 cycles in 1 minute. So what we will do? We will divide this mass flow rate into calorific value divided by 60. What is the number of cycles in 1 minute? The number of cycles in 1 minute is 150, right? And sorry, 150. And this is how we will get the mass of air coming into the cylinder in one stroke. This is how we will get the mass of air coming into the cylinder in one stroke. But are we interested in the mass? No, we want the volume, na? Volume of actual air. So how can we find the volume of actual air from mass? Well, there are two common methods to find the volume from mass. What is the first? We can use density. Density is what? Density is mass upon volume. So what is volume? Volume is mass upon density, right? So if we have mass and we divide it by density, then we will get what? We will get the volume of intake air. But in our case, they haven't given us the density, right? Nowhere have they given us the density. Then what can we do? So we will have to use the other formula. What is the other formula that is possible? Arey, you know na, PV is equal to MRT, right? PV is equal to MRT. Out of this, C, M is from here. This is our M. We know R is constant. We know T is what? T will be room temperature. Room temperature is how much? 20 degrees Celsius. That is what? 293 Kelvin. So we know the room temperature. Then what is the other thing that we need? We are going to find volume, right? So volume is not known to us. But do we know the room pressure, intake pressure? Yes, we know. It is 1 bar. They have given it to us. See, this is the first sum in which they have given us the room pressure also with room temperature. Why? Only to find this volume flow rate of air. Okay, so that is why they have given this. So using all this data, we can find the volume flow rate of air into the cylinder. We will substitute this volume flow rate over here. We know the swept volume pi by 4 d square L. We will substitute that and we will get volumetric efficiency. Okay, so that is how we can find volumetric efficiency. How are we going to find indicated thermal efficiency? Indicated thermal efficiency is what? Indicated power divided by thermal power. How can you find indicated power? See, they have given us indicated mean effective pressure. So if they have given us indicated mean effective pressure, what is the formula that we are going to use? IP is equal to Planck upon 60 into number of cylinders, right? Where P is what? P is indicated mean effective pressure. L is what? L is our stroke length. A is what? Area of the cylinder, which is what? Pi by 4 d square. What is N? N is the RPM. It is 300. What is K? K is 0.5 because it is a 4-stroke engine. If it would have been a 2-stroke engine, K would have been 1. What is the number of cylinders? Number of cylinder is 1 because it is a single cylinder engine divided by 60. So we can find indicated power. We already know how to find thermal power, fuel consumption rate into calorific value. So we can find thermal power, and if we know indicated power and we know thermal power, then indicated power divided by thermal power is what? Indicated thermal efficiency. So that is how we are going to do this. So first let us look at these two things, then we will come back to our heat balance sheet. Okay. So first of all, here is our thermal power. Thermal power is what? Fuel flow rate into calorific value. So mass flow rate of fuel into calorific value, it is per hour. So multiplying kg per hour into calorific value, we get it per hour, right? This is per hour. Dividing it by 3600, we get it per second. So it is 28 kilowatt. So thermal power is what? Thermal power is 28 kilowatt. What is indicated power? I just told you Planck upon 60 into number of cylinders. This is your indicated mean effective pressure. This is your stroke length. This is the area of your cylinder. This is the RPM. This is 0.5 because it is a 4-stroke engine divided by 60 into number of cylinders. So you get your indicated power. Now to find indicated thermal efficiency, you just have to put indicated power divided by thermal power. So you get your indicated thermal efficiency, right? So this part is done. What is the next part? We have to find the volumetric efficiency. Just as I told you now, what is volumetric efficiency? Volumetric efficiency is actual air intake divided by swept volume. So we can find the swept volume pi by 4 d square L. That is what I have done over here. It comes out to 0.053 meter cube. Now we have to find what is the actual amount of actual air intake, volume of air intake. So first of all, we have to find the mass flow rate of air. See over here, I have calculated the mass flow rate of air. Fuel consumption rate is 2.4 kg per hour. I divided it by 60 to get kg per minute. Air fuel ratio is 22. So what will be air consumption rate? Air consumption rate is fuel flow rate into air fuel ratio. Just now I told you mass flow rate of air is equal to mass flow rate of fuel into calorific value, right? So that is what we did, and we got how much? 0.88 kg per minute. We got it in hour, we divided it by 60 and we got kg per minute. So this is the air consumption rate per minute, but we are not interested in per minute, we are interested in per cycle. So we do what? We divide this air flow rate in minute by the number of cycles in 1 minute. Okay, sorry, this should be per minute, cycles per minute, right? So what are we going to do? What are the cycles per minute? Because this is a 4-stroke engine, 2 rotations make 1 cycle. Hence RPM multiplied by 0.5. So this is the amount of air intake per cycle. This is the amount of air intake per cycle. But this is what? This is in mass. We don't want it in mass. We want it in what? We want it in volume. So how do we convert from mass to volume? Just now I told you we use the formula PV is equal to MRT, right? So we will substitute PV is equal to MRT. We know what? We know MRT and P. We just have to find V. So we put V on this side and take P to the denominator. So V is what? MRT upon P. This mass flow rate came from here. This is the mass of intake air in one stroke. Okay. What is R? R is 287. That is constant. What is T? T is 20 degrees Celsius. So 20 degrees Celsius is what? 293 Kelvin. And what is pressure? Pressure is 1 atmosphere. And 1 atmosphere is how much? 10 raised to 1 atmosphere means 1 bar. And what is 1 bar? 1 bar is approximately 10 raised to 5 Pascal. So substituting all these values, we get the we get the actual amount of intake air. Okay, this is the actual amount of intake air. So substituting this value in this formula, see, volumetric efficiency is actual air intake in one stroke divided by swept volume. So this is our actual air intake in one stroke divided by swept volume. So what do we get the efficiency? Volumetric efficiency is 93.09%. Okay. So this is what we got for volumetric efficiency. Now we will look at the heat balance sheet. Okay. In heat balance sheet, these are the 5 things that we have to measure. Thermal power is easy, mass flow rate into calorific value. Engine brake power is easy, torque into 2 pi n upon 60. Heat loss to coolant is easy, MC delta T coolant. Right. We will look at how heat loss to exhaust gases can be calculated. But first we will take a look at these other 3 things. Okay, so thermal power is what? Thermal power is mass flow rate into calorific value. We calculated that beforehand only. We calculated it during this indicated thermal efficiency. This is what? Kilowatt. Kilowatt means what? Kilojoule per second. But they have told us to draw the heat balance sheet in what? Minute basis. So we multiply this. Kilowatt is what? Kilojoule per second. So we multiply it by 60. So we get 1680 kilojoule per minute. That is the thermal power. What is brake power? Brake power is torque into omega. Omega is 2 pi n upon 60. So substituting that values, we get 6283.19 watt, which is what? 6283 kilowatt. But kilowatt means what? Kilojoule per second. We want to convert it from kilojoule per second to kilojoule per minute. That is why we multiplied by 60. And over here, I am really sorry. This should be kilojoule per minute. Right, this should be kilojoule per minute, that is 377 kilojoule per minute. Then what is the heat loss to coolant? Heat loss to coolant is MC delta T. They have given us the mass flow rate of coolant. See over here, they have given us the mass flow rate of the coolant. Where is it? Yeah, mass flow rate of the coolant 5 kg per minute. They have also given us the delta T of the coolant water, which is how much? 35 degrees Celsius. So we know M, we know delta T, and we know the C of coolant water by heart, 4.18 kilojoule per kg Kelvin. So substituting these values MC delta T, we get the heat loss to the coolant, which is how much? 5 into 4.18 into 35, 731.55 kilojoule, 731.5 kilojoule per minute. See, this should also be kilojoule per minute. I have made that mistake. So that is how we got thermal power, we got brake power, and we got heat loss to coolant. We can substitute these values over here. We can substitute thermal power, we can substitute engine brake power, and we can substitute heat loss to coolant. Now we have to find out what is the heat loss to exhaust gases, right? So as I told you, to find the heat loss to exhaust gases in this case, we have to divide that exhaust gas into 2 parts. Okay, what are the 2 parts? One part is dry gases and one part is H2O, right? One part is dry gases and one part is H2O. To find the heat absorbed by the dry gases, it is very easy. Why is it very easy? What is the heat absorbed by dry gases? Q is equal to MC delta T dry gases. Okay, the heat absorbed by dry gases is what? Q is equal to mc delta T dry gases. So that part is very easy. But what is the mass flow rate of the exhaust gases? That part we will come. Just what is the mass flow rate of dry gases? Okay. What is the specific heat capacity of dry gases? It is already given to us. And what is delta T of dry gases? Array, delta T of dry gases is was exhaust gas temperature minus room temperature. So 410 minus 20, which is what? 390 Kelvin, right? So we know delta T of dry gases, we know specific heat capacity of dry gases. How are we going to find the mass of dry gases? Well, see, to find the mass of dry gases, they have given us some information. What is the information they have given us? That hydrogen is 15% of the fuel, right? Any fuel is made up of what? Any fuel is made up of CXHY, right? This is our fuel. Every fuel is a hydrocarbon. Out of this, what is the mass of hydrogen? Mass of hydrogen is 15%, right? And other remaining 85% is carbon. So using this logic, we are going to find out what is the mass of dry gases and what is the mass of water, right? So see over here what we have done. Yeah, see over here, heat loss to exhaust gases. What have they given us? What is the mass flow rate of fuel? 2.4 kg per hour. We convert that kg per hour into kg per minute. Sorry, over here it should be minute. So it is 0.04 kg per minute, right? This is the amount of mass flow rate of the fuel. What is the mass flow rate of the exhaust gases? You should know by now, exhaust gases are made up after the combustion of fuel inside air. Therefore, mass flow rate of exhaust gases is what? Mass flow rate of fuel plus mass flow rate of air. This is mass flow rate of fuel. How can we find mass flow rate of air? Mass flow rate of air is mass flow rate of fuel into air fuel ratio. So this is mass flow rate of fuel. This is air fuel ratio. So this is total the mass flow rate of exhaust gases. So this is mass flow rate of exhaust gases. But what have they told us? 15% of this fuel, 15% of this 0.04 kg per minute is what? Hydrogen, right? 15% of it is hydrogen. So 15% of fuel is H2, 85% is carbon. H2 is converted to H2O. So we can find out the mass of H2O in the exhaust gases. How can we find the mass of H2O in the exhaust gases? See, what is the mass of H2 inside the fuel? It is 15% of 0.04, right? 0.04 is the mass flow rate of fuel. Out of that, 15% is hydrogen. So multiplying it by 15 upon 100, it is hydrogen. That is how much? 0.006 kg per minute, right? What happens when hydrogen combusts? H2 reacts with half of O2 to form H2O. So 2 grams of hydrogen. What is the molecular weight of hydrogen? 2. What is the atomic weight of hydrogen? 1. See, atomic weight of hydrogen is 1 and there are 2 atoms in a molecule of hydrogen. So molecular weight of hydrogen is 2. What is the molecular weight of water? 2 into 1. Hydrogen is 1 and oxygen is 16. So 2 into 1 plus 16. So 18 grams. So what does this mean? That 2 grams of hydrogen produces 18 grams of water. 2 grams of hydrogen produces 18 grams of water, right? So what is the amount of hydrogen that we are burning? 0.006 kg per minute. So what is the mass of the oxygen that will be formed? Mass of the oxygen that will be formed will be what? 0.006 into 18 divided by 2. Because 2 gram forms 9 gram, na? Means 1 gram of hydrogen will form how much? 9 gram of water, right? That is exactly what we are going to do over here. See, we did that only over here. So 0.006 kg per minute of H2 will form 0.0054 kg per minute of water. So of our exhaust gases, what was the total weight of our exhaust gases per minute? Total weight of exhaust gases per minute was 0.92. Out of that, 0.054 is water, and the remaining is dry exhaust gases. Okay, so that is what we have done over here. 0.92 is total exhaust gas. Out of that, 0.054 is water. So what is mass of dry exhaust gas? 0.866, right? So this is how we get the mass flow rate of dry exhaust, and this is the mass flow rate of wet exhaust, or else you can call it H2O, right? So what will be the heat absorbed by the dry exhaust? MC delta T. This is the mass flow rate of exhaust gases. This is the specific heat capacity of the exhaust gases, and this is the delta T of exhaust gases. So putting in all these three values, we get what? 337.74 kilojoule per minute. This is the amount of heat absorbed by the dry exhaust. Okay. What is the amount of heat absorbed by water? The amount of heat absorbed by water is divided into three parts. See what is happening. See, let us look at how the temperature of this steam is changing. Okay. Let us say this is temperature, and this is what? This is time. Okay. As time goes on increasing, see, it is steam. Okay, here it is 100 degrees Celsius, and here whatever is the exhaust temperature, 410 degrees Celsius. Okay, initially what is happening? The steam is cooling down, right? The steam is cooling down. The steam will cool down till it reaches 100 degrees Celsius. Then what will happen? Then the steam will vaporize, right? It will remain at the same temperature, 100 degrees Celsius, as it is liquefying, sorry, as it is liquefying, and after condensing, as it is condensing, and after condensation is complete, again it will start cooling to 20 degrees Celsius, right? Again it will start cooling to 20 degrees Celsius. So there is heat lost in three ways. First of all, the steam is losing heat. Then what is happening? Then there is condensation. That is why we will use heat of vaporization. And then there is cooling of water, right? So hence heat absorbed by water is divided into three parts. First, this is MC delta T of steam from here to here. Then it is M into L, right? Because it is heat of condensation. And then it is again heat lost to water. So that is what we have done over here. M is going to remain the same in all three cases, 0.054, 0.054, 0.054. What is specific heat capacity of steam? They have given us the specific heat capacity of steam. Okay, somewhere they have given us steam specific heat capacity, 2.1 kilojoule per kg Kelvin. So substituting that value, over here. So substituting that value 2.1 over here, and delta T of steam. Steam is going from what? Steam is going from the exhaust gas temperature to 100 degrees Celsius. So 410 minus 100. What is the amount of heat lost in vaporization? It is mass flow rate of steam into heat of vaporization. What is heat of vaporization? 2250. That is also given to us. See, latent heat of vaporization is also given to us, 2250 kilojoule per kg. So substituting that value here, substituting that value over here, 2250, right? We get M into L. And again the water, now it has become into water. The water is cooling down. So mass flow rate of water, this is the specific heat capacity of water, and it is cooling from 100 degrees Celsius to 20 degrees Celsius. So it is going to 20 degrees Celsius. So this is the total amount of heat that is absorbed by the water or steam. This is absorbed by steam. This is absorbed by steam for condensation, and this is absorbed by the liquid water. So this is the total amount of heat absorbed by the water part of the exhaust gases or the wet exhaust, and this is the amount of heat absorbed by the dry exhaust. So what is the total amount of heat absorbed by the exhaust gases? It is the sum of these two, and this is the total amount of heat absorbed by the exhaust gases. Okay, so this is how this sum is to be solved. And now that you know what is the total amount of heat absorbed by exhaust gases, you can substitute that over here, right? You can substitute the total amount of heat absorbed by exhaust gases over here. Now the only thing left to find is unaccounted heat losses. And how do you find unaccounted heat losses? You take sum of these three and you subtract these three from 1680 and you get your unaccounted heat losses. Then you calculate the percentages. How do you calculate the percentage? 377 divided by 1680, 512.45 divided by 1680, 731.5 divided by 1680. This is how you calculate the percentages, and this is how you draw the heat balance sheet. Okay, so these are the things that you have to do. See, this sum is different because it had both things. It had volumetric efficiency also, and it had this exhaust gas divided into two parts, dry exhaust and wet exhaust. We had to calculate the heat absorbed by dry exhaust separately and heat absorbed by wet exhaust separately. And we calculated that and we found the total heat absorbed by the exhaust gases. And then we can draw this heat balance sheet. So this was the last sum on heat balance sheet that I solved. I think this is by far the most difficult sum because you have to understand the concept that how wet exhaust is going to behave, how dry exhaust is going to behave. Okay, so hopefully you have understood heat balance sheet, and if you have any questions you can always contact me. Okay, so thank you.